Okay, so yesterday we started the limit laws. We saw that with like a polynomial, we could use direct substitution. We also saw that if we are dealing with a piecewise function, that we have to be concerned about these border values. So you'll notice, of course, they were so lovely to us. They were picking the border value. Like if they pick any number that's less than 3, if you're approaching 2, you just plug 2 into that function. If you're approaching 7, you just plug 7 into that function. So it's great if it's not a border value, because those are continuous functions except at the border. So the border value caused an issue. So do you see how this does not have the little plus or minus notation? So that means we have to check, what am I heading to from the left? What am I heading to from the right? So let's write that down. So if I want to find the limit as we approach 3 from the left, those are the values coming in from the left or less than 3. So we're going to be focusing on the top function. Now the top function has an open circle when x is equal to 3, but that open circle would be at 3 minus 1 squared minus 5. 3 minus 1 squared is 2, 2 squared is 4, 4 minus 5 is negative 1. So it would approach that height of negative 1. Yes, it would have an open circle there, but as we're coming in from the left, we would be approaching negative 1. Now that's the left. Now let's talk about the right. The limit as x approaches 3 from the right is coming in from this side. So if we plug 3 into that, we get 6 minus 7 or negative 1. A piecewise function border, you have to check that the two border pieces are coming into the same height. I do not care if there's an open circle there. I will care when I'm dealing with continuity, but I'm not going to care when I'm dealing with a limit. A limit is what is we are approaching from both directions. So are we approaching the same thing? We sure the heck are. So because of that, the limit as x approaches 3 is indeed equal to negative 1. So only if they match will we say that the limit itself exists. So just be careful for a piecewise function. If it's not a border value, just pick the appropriate side that it's on and plug it in and you got it. But if it's a border value, those border values have to come in from both directions. If it has the plus or minus notation, you can just use the correct left piece or right piece. But if it doesn't have that little plus or minus, check both pieces, they have to match. Okay, are we good with example 9? Okay. So that brings us to something called the squeeze theorem. If we have two functions and f of x is always lower than g of x, then the limit as we approach any a will always be less than the limit in the g function. So if f is always lower than g, or less than or equal to g, then as we approach a, the limit as we approach a of both the f function and the g function will have that same relationship. So that's all that's saying. If this is less than, then the limits are less than. This allows us to use a squeeze theorem, which is essential when we have functions where direct substitution doesn't work. If we put that in the middle and we use two functions that direct substitution will work on the sides, the middle one, it'll kind of give us the answer. And so the squeeze theorem was used to help us with those functions where I don't know how to plug stuff in. And so that's where the squeeze theorem comes into play. So it looks like this. So look, we have this h function, which is higher than the g function, which is always higher than the f function. See that relationship? If that's the case, and h and f have the same values at a particular location, what's interesting is is then what we can do is we can just say, oh, that g function was sandwiched in between them. So at that location, it better have the same value of L that the other ones do. Now that only happens if our h function and our f function are meeting up at some exact location. But it just squeezes it in there between the two things. Now that's only helpful if the middle function, our g function, is a function that it's hard to understand what's happening to it. So it might have some trig stuff in it. It might have some zero denominators or something funky happen at that point. And when that funky thing happens, the squeeze theorem is going to allow us to kind of calculate the limit kind of in a sneaky sort of way. So the squeeze theorem just allows us to kind of calculate some funky limits. We're not going to use it very often. Maybe this assignment might be the only time you're going to see it. I even rarely will see it, you know, when we take like a chapter test or something. Maybe if I put on there like one that uses the squeeze theorem like as a bonus. It's not something that's used often, but it is something that is out there for more advanced math to use. So let's look at an example how the squeeze theorem is helpful. If you go to try to put 0 into this function, you get 0 times the sine of 1 over 0. Is 1 over 0 defined? It is not. So because of that, there's some things that we're going to do to fix it. Okay, so let me show you what we're going to do. Would you agree that the sine of anything, so let's just call it theta, is always stuck between -1 and +1, right? We've learned that the sine value, think of the unit circle, is always stuck between +1 and -1. Now, because it's stuck between it, that means that the sine of 1 over x is always stuck between +1 and -1. Any sine has to be a value between -1 and +1. That's what a sine does. It's a wave. Even the sine of 1 over x. Okay. Now, the next trick we're going to use is x squared, would you agree, is always a positive thing. So does it mess it up if I multiply x squared in an inequality? Does it hurt it at all? Of course it doesn't. It doesn't change. You know how that rule is, if we multiply through by a negative, we got to flip the symbol? Well, x squared is always positive. We don't have to flip anything. So let's multiply everything here by x squared. If so, we get -x squared is less than or equal to x squared sine of 1 over x, which is less than or equal to x squared. Okay. Now, we finally have something that is on each side of the thing we were looking at. It's squeezed between those two things. If you were to look at the graph of -x squared and +x squared, the one graph is always higher than the other, or touching, okay? So if you pulled it up in Desmos. So now we're going to do a trick. Let's take the limit as x approaches 0 of -x squared. And let's take the limit as x approaches 0 of +x squared. Now we learned through the rules of the limit laws that for a polynomial, we can use direct substitution for any value. So if you plug in 0 into -x squared, what you get? 0. If you plug in 0 into +x squared, what you get? So this is saying that the limit of this is going to be 0 as well. It's squeezed between those things. So if we were to pull up the graph, you would see that as we approach 0 of x squared sine of 1 over x, it is indeed heading to 0 from both directions. And it's just a result of the squeeze theorem that we could do something like that. It works a lot for trig functions because of the fact that we have that range of a sine and a cosine. So you'll see it used a lot for sine and cosine. It's just a little weird theorem that comes about because just the way limits work. Okay, so your homework is right here. It is, I don't think, due till either Friday or Saturday. Check Google Classroom. I think it's due Saturday. And you have all class time tomorrow to work on it. If you're allowed to use direct substitution, go for it. Remember, if you get 0 over 0 when you do direct substitution, that means you have to manipulate the algebra to get it to work. So that's the main thing to take away from this assignment. So factor it if you can, cross out factors. Square roots, use the conjugate. Fractions, bring them together. Try all those things. So there you go, there you go, there you go. Do your thing.